This stuff not easy, so follow along carefully. Some of it is. Range is easy. Just follow along. You might want to jot down a few other things as we go through it. We're going to move sort of quickly though. Range, again, what we're covering, how data varies across the whole thing. All right, before we were talking about just what's in the center of the data. Don't have me taking those before the end of the year, okay? No. I got an eBay account. I sell all kinds of stuff. We were talking about the center of the data. Now we're talking about how it goes across the data. How it varies. Range is just the maximum minus the minimum. Real easy. Sort of helpful. Bad thing is, it only uses two pieces of the data. So you only really get to see the high and the low. What could screw that up?
Outlier.
If you have an outlier, if you have something that's really high or really low. Alright? And we did this example. What's the lowest number here?
37.
37. What's the highest number? 47. 47 minus 37 is 10. That's your range. Nothing really hard about it. So range is $10,000 if I would have read the problem and seen what it said. Deviation. Deviation is the difference between the data entry, so each piece of data, and the mean of the set. Remember, mu is the mean of a what? Population. X bar is the mean of sample. X just stands for each piece of data. So Riley's piece of data, then Ben's piece of data. Those are each X's. So the deviation is just what each one of those deviates off that piece of data. You may have, I'm trying to think which test does it. I think the ASVAB. All of you took the ASVAB at one point, unless you were out that day, but everybody takes it. It's a military test, right? So, huh?
No, you signed up to take that.
Oh, is it?
There's
Is that
only
way now?
like 4 of us.
Really? So it used to be everybody had to take it. So now they switched it up. So I didn't realize that. Should pay more attention, I guess. On the ASVAB test, I think when you get your grades back, it usually has a line on it, and then it does something like this, and it puts an X there. Then it's got like this, and puts an X there. Then it's got this, and it puts an X there, and it's got this, and it puts an X there. And you know, if it's Sean's paper, then all the X's are like way up here somewhere. And what it's telling you is, hey, you were that far above or below the mean in that certain area. When I took it when I was here, the recruiters came in. Apparently I did fairly well on it, and they came in and said, you know, what you should do is you go into atomic submarine stuff in the Navy. And I'm like, yeah, right, that ain't enough submarine. I don't like water. So to find the deviation of each one of these, first thing we have to do is find the mean again. What's the capital N stand for? Number in the population. What's the small n stand for? Number in a sample. So just make sure you're keeping all those symbols straight. These are our deviations. And we talked about this last time. When you add all those deviations up, what are they going to add up to? That's not real helpful. All right? So what do we do with each one of those deviations? You square each one of them. And that's what we have to do on each one of them. And then we're going to use that. they're like a distance, a distance that you are from the mean, all right? But you could be above or below. So when we want that distance, we actually want the positive number. The sum of all the deviations is always going to be 0. Instead of using that, and I think we wrote this down last time, this is very important. Sum of the squares, which is abbreviated SS with a little subscript X on it. So the sum of the squares, and this is the formula for that. That symbol is sigma. So sigma is just a sort of like an O with a little tail on it. It's just a Greek letter, and we're going to use it. Just that's a Greek letter. Also, I think is that epsilon? Is that what that is? And we use it for summation. Sigma we're going to use for something else. What was the other Greek letter that we've used so far? Mu. Sorry, I couldn't remember. Mu. Population variance and population standard deviation, both these very, very important. Probably the ones on the next slide or coming up are a little more important than this because it's a sample. And it doesn't really matter which one you know for sure. Don't do it. Why do you want to? You just want to be mad at me, don't you? Not just my sophomore year, but the other senior class, or the others.
Your super senior class.
Wow.
You needed to take that.
I was thinking that.
Yeah, I did.
Yeah, I won't lie. I'm glad I got out of there.
I'm not.
Yeah, it's
I gotta do actual math.
This is even actual.
There's numbers.
This is hard.
If I'm in transitional math, bro, I'm like, how many apples does Julie have? Man, this don't mean nothing. I can go work.
So on this population variance, you're going to find that sum of the squares and just divide by how many are in the population. And then to find the standard deviation, all you do is take the square root of that answer. So don't make this harder than it is. We started off and we were doing the little charts and finding each thing on the charts. We will talk about today, and I think we talked a little bit about it last time, how to plug it into the calculator and do all that. I'm going to skip, this is what I skipped over, wasn't it? This is just telling you the steps how to find the population variance and standard deviation. I won't skip over the one about samples, same steps though. So on our chart, we got each of our X's listed here. Again, we got Riley's number, Ben's number, so on, all the way down through here. We find the deviation of each one. That was those numbers. And then we square each one. That's these numbers. Once we square them, now they're all positive. And then what we want is this total down here. So as you're doing this, if you're doing this out longhand on your calculator, my suggestion is you type in this number squared plus this number squared plus this number squared, and don't even put this column in here, just put the total, as long as you can keep it straight in your head and don't mess it up. So that's the sum of the squares. That sum of the squares is going to help us to find the variance. All we do once we have that 88.5 is we divide by how many numbers are in the population, and we get 8.9, and that's the variance of the population. Again, for now, variance, not real useful. Later on in the year, we'll do more with variance, but for now, variance is just sort of a number we find, and we really don't do a whole lot with it. How do we find the standard deviation once we know the variance? Just take the square root. Standard deviation is 3. Now, what the standard deviation says, we have our mean, it's right in the middle, and standard deviation, and we're going to talk about this as we go. I think we sort of got to this, but didn't get through it completely. With standard deviation, if we go 3 standard deviations above, 3 standard deviations below,
It's very unusual.
all the data should fall in that range. For every set of data in the world. All right. Now, very unusual is if you have what? If you're more than 3 standard deviations away. So if you're out here somewhere with a piece of data, it's very unusual. If you're between 2 and 3, then it's unusual. More than that, it's very unusual. And we'll talk about that a little bit. The sample ones. These are very important. Notice with the sample, the only difference in the formula is, well, X bar and mu changes. But the other difference is instead of using N, the capital N, we use N minus 1. I'm not sure why that is. I think we said that Lily, when she becomes a great statistician, she's going to come back and tell us, right? Good idea. Throughout the year, we're going to do stuff like this. This will tell you steps to do. Step 1. Find X bar, find your mean. Step 2, find your deviations. Step 3, square each one of those. Step 4, add them all up to find your sum of the squares. Step 5, take that answer and divide by N minus 1. That's going to give you your variance of the sample. And step 6, to find the standard deviation, just take the square root of that answer. Now, we ended up last time, instead of doing all these steps, what did we do? We just plugged it into the calculator, plugged in the list in the calculator. What does the calculator not tell you? It doesn't tell you the range or the variance, all right? So you're going to have to find those yourself. So with the calculator is going to tell you, I'll write this down, calculator tells you your S, your standard deviation. What do you got to do to find the variance?
Square.
To find variance, square the S. So make sure, if we're doing it out longhand, you find the variance first, then take the square root. If you're using your calculator, it's going to tell you the square standard deviation, and then you gotta square it to find your variance. So it's sort of backwards. We did this one together, didn't we? Did we do this one on the calculator? Did a couple. So if I'm doing this out longhand, oh, this is the one we did the first time, didn't we? And we did it out longhand. Get that, 9.8, square root of that's 3.1. This is your variance, that's your standard deviation, and you put it into your calculator and do it. This is the one that's stuck in the calculator with. So if we stick this in our calculator, we can do it. Just make sure, be careful when you're plugging it in. If you mess up, hit a wrong button somewhere, forget a decimal, it's gonna mess up your all of your numbers. If you didn't write this down last time, very important. Did we figure out anything with the Casios? Were they a little different?
Yeah.
So what'd you have to do that was different?
I don't remember exactly what they said.
You still know how to do it? Wade, you figured it out with your Casio last time?
Yeah.
Alright, so hit stat, edit. Gonna punch in the data. In other words, all you're doing is putting it in some list. Alright? Once we get it in the list, go back to stat, hit stat again. Now we're gonna hit calculate 1 bars, and once you have one variable stats, you hit enter, and this is gonna pop up on your screen, and then you gotta hit second in whichever list you put it in. Then it's gonna look something like that maybe, if you put it in list 1. Then you hit enter. And it tells you X bar. What else did we say it tells you? Sum of all the X's, is that right? And it tells you sum of X squared.
Median.
And it told you what?
Supposed to be
Median. I think it was quartile 1 first, wasn't it? Then median, which is quartile 2, then quartile 3. What else does it
high,
say?
low.
Tells you the lowest number and the highest number, so you have to subtract them to get the range. Can't remember what, key one I forgot. Tells you S sub X and it tells you sigma sub X. What's the difference in the two? S is for sample, sigma's for population. So it tells you the 2 standard deviations. Probably something else in there that I forgot. Should just flip to this slide and it will tell us.
Kurtosis.
It's all right there. Oh, it tells you how many's in the set, so on and so on. This is if you're doing it on an Excel spreadsheet. It looks something like this. The mini tab is a computer setup that we can't get to online anymore because our books are so old that many tab setup's probably outdated. It's not there anymore. Your standard deviation always has to be greater than or equal to 0. Can't be a negative. Standard deviation is a measure of variation of all the values from the mean. So you're figuring out how much each value on the average varies from the mean score or whatever it is you're dealing with. The units of the standard deviation are always the same as the units of the data value. So if we're dealing with money, then our standard deviation is money. The value of the standard deviation can increase dramatically with the inclusion of 1 or more outliers. So outliers really mess up standard deviation. That's why later on in the year we're going to deal with those outliers and sort of push them out of the set of data to try to better look at what's actually going on in all of the data. Just went over, I'm not sure why I have 2 slides that say the same thing. Notice with the standard deviation, if the standard deviation is 0, then what do you know about all the data? It's all the same. Every number was the same. All right. If the standard deviation is something like 1.2, notice it's all sort of boxed right there together. As the standard deviation gets bigger, it spreads out the data more. Or means the data is spread out more. These are just the symbols. Make sure you know all these symbols. I think might have a symbols test coming up here really soon. So Michael, you'll walk through the door and I'll say, put everything away. And tell me what each of these symbols mean. And I'll just give you a piece of paper and you just gotta tell me what each one means. Be careful on something like this. What are you gonna write down for that answer? If you just put mean, think I'm gonna count it? Mean of the sample. You gotta tell each one whether it's a sample population and the symbols.
So just remember that chart.
That's basically all we've had so far. Except for, I forgot something here. This should be SS sub X. That's that symbol. So we started this, I think we got through some of this last time.
Chevy chip.
Did we get through the range rule?
Yeah.
This is if you just wanted to estimate, all right? If we wanted to estimate, if we knew what the standard deviation was and we wanted to estimate the range, what the highest and lowest number is, then we could use this, 4 times S. The more important one is this. If we know what the range is, so if the highest is 10 and the lowest is 2, we subtract those 2 and get 8 and divide that by 4. We're saying the standard deviation should be somewhere around 2. Not an exact number, but it's somewhere close. So that's it's called the rule of thumbs. Anybody know what, when you say the rule of thumb, what that means? Yeah, you're just sort of, what it was a long time ago. People would do stuff like this to see how far something was. And it was called the rule of thumb. So you go, okay, I think Leah is about this far from me. The empirical rule, this is the one that's important. Very, very important. When I get to this, once I get all this up here, these 2 middle ones, 34% each. That's 1 standard deviation away from the mean. Next 2 are 13.5%. Then the last 2 are about, we'll usually go 2.5% on these. So you might, on your thing there, instead of 2.35, you might just put 2.2. It's going to be somewhere close to that. And we'll round it off here and there just to make it a little easier. All the data, 68% should fall within 1 standard deviation above or below the mean. 95% should fall within 2 standard deviations. And 99.7% should fall within 3 standard deviations. Well, that leaves 0.3 for each one of these sides out there. Not very many people, or not very many pieces of data fall in that range and outside the 3 standard deviations. And that's what Phoenix was talking about a little while ago. All right, on this, I think we sort of skipped over this last time. I don't want to skip over this because I want you to know that you've got to be able to do this. So, if nothing else, just watch. I would write it down, but I don't want to force you to write down that whole thing. What you're gonna do with this, and what you gotta be able to do on problems, as we're doing them in the book, is you got to be able to draw this stuff. So I'm gonna draw myself a little number line here. And on that number line, I'm gonna put that, normal curve, or that bell curve on there. This says, in a survey conducted by the National Center for Health and Statistics, the sample mean height of a woman in the United States, ages 20 to 29, is 64.3 inches. Where am I gonna put that 64.3 inches? So you gotta be able to draw these. 64.3 is gonna go right there in the middle. Normally, what I'll do once I have that 64.3, once I have the mean, I'm gonna go 3 that direction, 3 that direction. Alright? To get these higher ones, what are we gonna do, Phoenix? You're gonna add. It says the sample standard deviation is 2.62. So to go to this next one, what am I gonna put? Add on 2.62, right? So 60, what is that? 60, it's 66.92? Is that right? Then what are you gonna do to get this next one? Add 2.6 to that. Get back to it. Add 2.62 to that, so that's what, 69.54? Is that right? And then what do I do with that? Add another 2.6 to that. Now, when we're drawing these, you don't have to be this exact, all right? Because you're usually drawing them for yourself. So we don't have to be exactly, so if I do the next one, and I'm gonna add 2.6, I say, all right, that's gonna be about 72.1. That's pretty close, and it gives me the right idea. I just left off the last number. How do I get these numbers going out the other direction? Subtract. So 64.3, if I'm just gonna estimate it, 64.3 minus 2.6, what is that, about 61.7, is that about right? 61 point, is that wrong? Is it close? Thought I heard somebody wrong. Then minus 2.6, that'd be about 59.1. And subtract off another 2.6, that'd be about 56.5. This is my mean right here. What do I know about what percentage of the women should fall in this range? Should be 34%. How about the women that fall in from here to here? 13.5. And that's all we're using. Now let's read the problem and see what it says. Average the percent of women whose heights are between 59.06 and 64.3 inches. So 59.06, I'm guessing that that's this one right here that I rounded off too much. And 64.3. That's right there. How would I figure out what percentage of the women should fall in that range? So we get about 47.5%. So almost 50% of the women in the world fall in this height range, 59.1 inches to 64.3 inches. So 59.1 to 64.3. So let's see what we got here. We got 1, 2, should we count Phoenix? 3, 4, 5, 6, 7, 8. We got 8 females in the class. We're saying 47.5%. Somebody help me out with your calculator. What's 8 times 47.5%? I'll change it to a decimal. Change the 47.5 to a decimal. 0.475. 3.8. So if we went around and measured all the females in the class, we're guessing that 3 to 4 of them should be within those two heights. All right? Anybody know what 59.1 inches is? I don't know, is that right?
5 foot.
Five, cause 12 times 5 is 60, so it should be like 411.
So if we divide it by 12, how many 12s are there in 59?
4.9.
4-9.
I think that's short.
So not 4.9, now you gotta be
4
careful.
foot 9.
No, be careful, because does that decimal translate,
11 to 5
does
three.
.9 translate to 9 inches? No, because decimals are in tens and our inches are in 12s. So 4 foot, Riley was right, it's 4 foot and how many inches? So about 4 foot 11, about 64.3 inches.
To 5'3".
5'4", because 5 times 12 is 60, right? So there's about 4 inches left over. So we're saying that between 4 feet, 11 inches, up to 5 foot, 4 inches. If we measured all the girls in here, would we have about 3 or 4 of them, you think, that were in between that? I don't know. How many of you fall in between that? 1, 2, 3. Sean, don't raise your hand, man.
I don't fall in there actually. I don't fall in there.
4, so there's 4 of you?
But I know there are 20 to 20. I have 8
My mom falls in between there. That's-
Sim's at least 5'5".
She's older than that, but
Dang.
she's still.
Dang.
At least.
That's 5'5".
I mean, at least.
And he's the chief of
At most, Sim, at most, you're gonna.
Short king.
Chevy Chevs theorem. All right, with this, the bell curve, I've been saying that it fits for everything. It doesn't actually fit for everything. All right, so they'll tell you if data is normal or not. If it's normal, then that means it fits the bell curve. All right, it's going to fit that empirical rule. A lot of data doesn't fit that. So you might have some data that looks like this, and it might be where all the data is down here, and then there's some other data over here, not very much. It might look something like that, where this doesn't fit a bell curve. We can use this theorem to estimate how much of the data falls lower than a certain spot. And the way we do it is this K right here just stands for the number of standard deviations. And this isn't hard. If we have one standard deviation, we could do this, and you might write this down and you're always going to get it right. If we have one standard deviation, then we just, sorry, I forgot my minus sign. We put that in there. What's 1 squared? 1. 1 divided by 1? What percent of the data are we saying falls below 1 standard deviation? 0%. If we have 2 standard deviations, what's 2 squared? 4. 1 divided by 4? 3/4. What's 1 minus 3/4? 1/4, which is what is a percentage? 25%. So we're saying 25% falls 2 standard deviations or more below it. And then if we have 3 standard deviations, what's 3 squared? 9. 1 minus 1 9. Do that on your calculator real quick. What's 1 minus 1 9? Point what?
ABC button.
Can't find the ABC button, what could you do? Could just add the parentheses, could just divide it. 1 minus 1 divided by 9, and it'll do it.
So it is 0.88.
0.8 repeating, which is about what is a percentage? 89%. So if we're at 3 standard deviations, about 89% of the data is going to fall below that. So if we're looking at a set of data and it has 52 pieces, if our n equals 52, and we want to know how many people fell at 2 standard deviations or below, we would just take 52 times 0.25. And that's going to tell us about how many of the pieces of data fall at or below that. So Chebyshev's it's nothing really hard. It's not something that we use a whole lot, but it just works for anything. So if you're doing something and you don't know whether it's normal or not, then you can say, hey, I expect that almost 90% of the data is going to fall here or down. The age distribution for Florida is shown in the histogram. Apply Chebyshev's theorem to the data using K at 2. What can you conclude? So if I do K at 2, what was that? That came out to be like 25%, didn't it? So we're guessing that 25% of the data is going to fall at or below 2 standard deviations. If we look right here, our standard deviations, 24.8. Our mean is 39.2. And all we're going to do, how many standard deviations do we want? 2. So we just add that on twice. Let's go to this next slide. So we do this, we got all this, and minus 10. Use 0 since the age can't be negative. If we go back, we look at this. We went down too far when we subtracted off. Can you be 0 or below 0 as far as your age goes? It doesn't work too well. Alright. Not a big deal. It's just telling you what's going to be, I'm sorry, I've been saying at or below. I meant at or above. Standard deviation of grouped. I know we didn't get to this. If you're doing something like a frequency distribution, so we've done our frequency distribution charts. If we have something like that, it can't be in classes. It'd have to be each number separately. So it would have to look something like 0, 1, 2, 3, 4, 5. And then we'd have our frequency. Maybe there's 10 here, 9 there, 5 there, 8 there, 7 there, 2 there. I don't know, just making up numbers. So if we have something like that, we can use this. Now it looks a whole lot harder than it really is. Now, I was doing this, if I was doing this chart, instead of doing it using this formula, what I would do, this is telling me that in my set of data, I have how many zeros. So, I would use my calculator still, and guess how many zeros I put in? 10. How many ones would I put in? 9. 5 2s, 8 3s, so on and so on. And I would just put all those numbers in my list, and then we can do it the way that we do everything else. alright? If you don't wanna do it that way, it take a little longer, cause you gotta punch all that in. I don't know which one takes longer, punch it into the calculator or doing it out this way. If we do it out this way, then you're just gonna add to our chart. And what we're gonna add, we're gonna find the mean, the mean. Then we're gonna find the standard deviation, or the deviation of each one. Then we gotta times that each by how many there are in that set. So we find it for 0, 1, 2, 3, all those, and then we just multiply that answer times 10, then times 9, then times 5, then times 8, so on and so on. Then once we have all that, we add them all up, then we divide by n minus 1. Well, our n here, we'd have to figure out what the frequency is here. It looks like it's 15, 30, like 41. So we divide by 41, 41 minus 1. So we divide by 40. That's going to give us our standard deviation. When a frequency distribution has classes, if we wanted to do it with classes, so if this wasn't 0, 1, 2, 3 all separate like that, if it was 0 to 3, then 4 to 7, then 8 to so on, so on, so on, all the way down. If it had that, then what we'd have to do is find the midpoint. And you find the midpoint of each one, and then use that as your x for each one. We're not going to do a whole lot with this. Most of them will be just straight out, hey, here's a set of numbers. Use them, plug them into your calculator, and do all this stuff. So with this one, if we're doing this one, we grouped it. Notice it's got a bunch of 1s and 0s and 2s all the way up to 6s. You collect a random sample of the number of children per household in a region. Find the sample mean and the sample standard deviation. Again, you could just take all those numbers and plug them into your calculator and do it that way instead of grouping them. If we do group them, it's going to work out like this. We got 0 times 10, that's 0. 1 times 19 is 19. 2 times 7 is 14. 3 times 7 is 21. All I'm doing is multiplying all that, multiplying them all together. The x times the frequency. Once I have all that, I divide. So the sample mean is 1.8. Once I have the sample mean, I'm going to add these other rows to my chart. So I got the sample mean, and I just subtract each one of those to find our deviations. Then I'm going to square each of those deviations. Then, instead of adding all those up like we did on the others, now we got to take each one of those times the frequency. So we got to multiply those two answers. And we get these, and these are the ones that we want to add up. And that's like the sum of the squares that we've talked about before. Then we take that number, that 145.40. We're going to divide it by n minus 1. I don't remember what n was now. Let's see, that's 29, 30, 44, 45, 46, 50. So we're going to divide it by 50 minus 1. That's going to be 49. And then whatever that gives us, that's going to be our variance. Then we have to take the square root of that, and it comes out to be 1.7. So if we're looking at that, if we look at it on our normal curve again, our mean was like 1.8, right? Is that right? To get standard deviations going up, we add 1.7, be 3.5. Then we add 1.7 to that, that'd be 5.2. And we add 1.7 to that, and that'd be 6.9. We subtract 1.7 down here, that'd be 0.1. Subtract 1.7, we're at negative 1.6. Subtract it from there, that'd be negative 2.3. How many families are gonna fall in that range down there? How many have negative 2.3 kids? Probably none,
Hope not.
all right? Hopefully not.
How do you have negative?
Yeah, that's it. So, sometimes it doesn't work out real well because of the negatives, but coefficient of variation, last thing here, I think. Coefficient of variation describes the standard deviation of a set of data as a percent of the mean. Can use to compare two sets of data with different units. So if you're trying to compare boys to girls, and they have completely different numbers and different units, you can find the coefficient of variation for each, and then compare those two numbers to get a better idea of how the two are related. The girls are smarter than the boys, or the boys are taller than the girls, or whatever.
Not even. Feels short. It's true. Drink my milk.
But baby,
Nope.
not
Never.
growth.
Nope. I'll never stop big. Ever. Ever.
They just keep getting shorter.
You're looking like sick, you see?
No, babe, I smoke cigarettes.
Yeah, 'cause at least you look cool doing it.
Doesn't the bathroom, don't you like the smell of just tobacco better than the smell of strawberry? Burnt strawberry? I can't smoke either one of them. It's very nice. I'll protect your lip pillow. Have a zinni. Have a chaw on the bottom and a zinni in the top. What is that?
The formula for population and for, and this should be an X bar here, the bar is moved way up, that's not an equal sign. So just, I don't wanna put another bar in there because it's gonna confuse it even more. So for population, you're just using mu on the bottom. For a sample, you're using X bar. Just try to rewrite that. Coefficient of variation equals S over X bar times 100%, that's for a sample. And again, all this is, it's a number that we can sort of switch or use any data and give the CV for it, and then we can compare two completely different things. So, how apples grow compared to how oranges grow. Well, you can't really compare those two things as normal. So you can switch it to this and say, change it to a percentage and sort of compare it. Say, okay, apples grow better in Ohio than oranges do because of the CV. So if we have this heights and weights of a basketball team, if you have your height and your weight, two completely different measurements. Can't really compare the two. You can't say, oh yeah, somebody that's 72 inches tall is always going to be 180 pounds. That's not true, because I'm about 72 inches tall, and it's been a long, long time since I was 180 pounds. So you can't compare the two just that way. Table shows the heights in inches, weights in pounds of members of a basketball team. Find the coefficient of variation for the heights and the weights. Then compare the results. Spelled wrong in the other one too. So we just have all those numbers. I'm just going to go through this. our coefficient of variation, if we find what mu is. This time we're doing it as a population just because it's the whole basketball team. For the heights, mu ended up being 72.8. The standard deviation we found, we divide that standard deviation, divided by that, and then times by 100, and it comes out to be about 4.5%. So that's the CV for the heights, 4.5%. That doesn't mean a whole lot all by itself, but if we do the weights, what did it do here? Weights get. All right, so the weights, if we do that, that's about 9.4%. So we got 4.5% for the heights, 9.4% for the weights. What do you think that means about our basketball team? How would you compare them? What do you know about the CV for the weight compared to the CV for the height? The weight's a higher percentage. What do you think that means about our basketball team?
We got a fat basketball team.
That probably means we're little on the chubby side, maybe. All right, so what we covered, find the range. Again, the main thing here, variance and standard deviation. We're going to be using those all year long. The empirical rule, those are the two main things that we covered today, finding those things. Your assignment, and we already do some of these.
No,
Wasn't it?
we didn't do.
We did 11 through 14, didn't we?
You gave me 9, 10, 28, 33 to 37, 39 through 43. That's the one you gave me on Thursday.
Really?
Well, I asked him for next class's homework, and that's what he gave me.
So this should have been it, my fault. You just gotta add a few to it, right?
So I did 9 and 10, and I didn't have to do either of those.
You want me to add them on there?
No.
Did you even do them?
Yeah, I did.
All of them?
No, I didn't do all of them. I didn't know what I was doing. We didn't do the notes for him yet.
So that's the assignment. We already did 11 through 14. With 11 through 14, my suggestion might be though, because we did them out longhand, might want to try them using a calculator, just to make sure you know how to punch all that stuff in. Make sure you're getting used to it, just to practice.